Today, I'm going to discuss a very important transition or change in organic chemistry. This change, this type of isomerism, is known as the Keto-Enol Tautomerism. The tautomerism is a special kind of isomerism which occurs due to the transfer of proton, and Keto-Enol Tautomerism is the tautomerism or the isomerism or the conversion of a ketone to an enol by the proton transfer. Now, what is ketone and enol? We will see them a bit later. This reaction goes a bit like this. On the left side, I have shown a well-known ketone, or I can say a simple ketone called acetone, and on the right side, I have shown its enol form. It has just been generated by the transfer of a proton. Now you can see both of them has the same molecular formula but different structural formulae, so they are structural isomers of each other, and this special kind of isomerism which arises due to the transfer of proton is called tautomerism. Now let us talk about a ketone. Ketone is an organic compound having carbon atoms on either side of a carbonyl group. So here is the simplest ketone, which has a carbonyl group in the center, and it has attached two methyl groups to that carbonyl group. This is called acetone 2-propanone or propan 2-one. There are some other examples of ketones like 2-butanone or butan 2-one. Then comes the pentan 3-one or 3-pentanone. Then comes the acetophenone, which has a phenyl group on one side and a methyl on the other side. Then comes 1,3-diphenyl propan 2-one, which can be also regarded as the dibenzyl ketone because it has two benzyl groups on either side of the carbonyl group. And then comes the acetophenone, which has two phenyl groups on either side of a carbonyl group. The benzophenone is different from rest of the ketones we have discussed so far. So this is because it doesn't have the hydrogen attached to the carbon, which is directly attached to the carbonyl group. Now this is important. Let us see how. So let us consider a ketone. So it has many carbon atoms on one side of the chain and only a single carbon atom on the other side. So we can see the carbon atom directly adjacent to the carbonyl group is called the alpha carbon, and the carbon atom one carbon away from the carbonyl group is called the beta carbon, and the carbons which are 2 carbons away are the gamma carbons, and those which are 3 carbons apart are called the delta carbons, and the hydrogens attached to them are named respectively. For example, the hydrogen attached to the alpha carbon will be known as the alpha hydrogen. So we can say one thing, that the ketones with alpha hydrogen will undergo keto-enol tautomerism. Now note my words, I am talking about the alpha hydrogens, not the alpha carbons. So let us see in our examples which carbon has the alpha hydrogen or which ketone has the alpha hydrogen and which doesn't. So acetone has 6 alpha hydrogens, 2-butanone has 5 alpha hydrogens, 3-pentanone has 4 alpha hydrogens, acetophenone has 3 alpha hydrogens, and dibenzyl ketone has 4 alpha hydrogens, while the benzophenone has none of them. So benzophenone is non-enolizable ketone. It is a ketone which cannot be enolized. It cannot be changed into its enol form. After discussing the ketones, let us now discuss the enol. It comes from two words, alkene and alcohol. The ene of enol comes from alkene and ol comes from alcohol. So we can say that the enols are the organic intermediates or the molecules which have alkene and alcohol functional groups at the same time. So they can be regarded as intermediates because usually the enols are far less stable than their ketonic counterparts. In some cases, they can be regarded as molecules because in these cases, the enol is more stable than the ketonic form. This happens usually when the alkenic part is a part of an aromatic ring. So let's take an example of phenol. Phenol is such an enol in which the enolic form is far more stable than the ketonic form because the alkenic double bond is a part of an aromatic ring. Now let us move to the enolization process. Enolization is the process of conversion of an aldehyde or a ketone to an enol. So let us start with an aldehyde. The simplest aldehyde which is enolizable is acetaldehyde. And acetaldehyde is enolizable because it has the alpha hydrogen. The alpha hydrogen is acidic, which can be abstracted by the lone pair of electrons of oxygen. So the lone pairs of electron of oxygen will attack the hydrogen, the alpha hydrogen, and the carbon hydrogen bond will be shifted to the carbon carbon bond. The two carbons are different because one of them is the carbonyl carbon and the other is the alpha carbon. And the carbon oxygen double bond will next be shifted to the oxygen, and we will get the corresponding enol, which is ethanol in this case. This ethanol can be reverted back to the ketonic form or the aldehydic form. So what is going to happen here is the carbon carbon bond will be shifted to the hydrogen which is attached to the oxygen, and the oxygen hydrogen bond will be shifted between the carbon and oxygen to revert back the carbonyl group. Now let us take an example of acetone. Acetone is also an enolizable ketone because it has two, or we can say it has 6 alpha hydrogens. These 6 alpha hydrogens are present on two different carbon atoms on the either side of the carbonyl group. So the process will be the same, but we can simplify it. We can say that the carbon oxygen bond will be shifted between the oxygen and the alpha hydrogen, as we have shown here, and the carbon hydrogen bond will be shifted between the alpha carbon and the carbonyl carbon. And what we will get the corresponding enol. The corresponding enol can be reverted back to the parent ketone by the process as I have told you before. Now let's take another example of pivalaldehyde. The pivalaldehyde has a tertiary butyl group at one side and a hydrogen on the other side. The tertiary butyl group has no alpha hydrogen, and the hydrogen attached to the carbonyl group is not alpha at all. So this aldehyde is not enolizable. There is a problem with the uncatalyzed enolization reaction, and this problem is the enolization is very slow process. This process is slow, obviously, because the ketone, the more stable form, is being converted into the less stable form, the enol, and there is a very small fraction of the enol in the equilibrium mixture, and this equilibrium takes too long to establish. The same equilibrium will be the same concentration of enol can be generated earlier than the uncatalyzed enolization reaction by using a catalyst. The catalyst can be an acid or a base. So let us see first the acid-catalyzed enolization reaction. So we can start with an acetone molecule, as we know that the acetone molecule has a carbonyl group which has an oxygen, and the oxygen has lone pair of electrons. These lone pair of electrons can capture a proton from an acid, and this enol, then this carbonyl group will be rendered more electrophilic, and in this case the alpha hydrogen is now more acidic. There is a greater chance of delocalization of carbon hydrogen single bond across the carbon oxygen double bond. So here we have a water molecule which can now extract the alpha hydrogen, and the carbon hydrogen bond is being shifted between the alpha carbon and the carbonyl carbon, and the carbon oxygen double bond will be shifted to the oxygen. So in this way there will be the generation of an enol. So now let us see the base catalyzed enolization reaction. The base-catalyzed enolization reaction, let us see it for the same substrate, and the base-catalyzed enolization reaction will first, the base will first attack on the alpha hydrogen. As I said earlier, the alpha hydrogen is acidic in this case. The alpha hydrogen is acidic because this hydrogen is capable of being lost in the form of hydrogen positive ion, and which will be abstracted by the hydroxyl ion, and the carbon hydrogen bond will be shifted between the carbon carbon double bond, the carbon carbon single bond, and the one of them is the alpha carbon and the other is the carbonyl carbon, and the carbon carbon double bond will be shifted to the oxygen. And then what will we get? We will get an enolate. It is not an enol because oxygen has no hydrogen attached to it, but there is a negative charge on the oxygen, so such a species is known as the enolate. And this enolate will capture a proton from water and will regenerate the hydroxide ion, and the enol will be formed in this reaction. So overall, enolate is the main intermediate, because whether we have the ketonic form which has the alpha hydrogen which is acidic, or we have the enol, the oxygen attached to the hydrogen attached to the oxygen is also acidic. So from both sides, from from left, if we see that as we have seen earlier, from the right side, that it will generate an enol by the abstraction of alpha hydrogen, and from right side we can see the same thing is being done in another way. The oxygen hydrogen bond is being broken and the hydrogen is being accepted by the hydroxyl ion in the form of an H positive ion, and the oxygen is getting the negative charge and enolate is being generated. Now this reaction is very important. Enolization is a very important reaction because it is the first step of many useful chemical reactions. So some of them are Aldol condensation, Darzen condensation, Favorvskii rearrangement, and the Michael addition.